In this final video in this series, I'm going to have a look at some other second order circuits. We'll start with this one. Here again we've got a single resistor, a single capacitor and a single inductor, but I've now arranged them so that we're taking the output over the capacitor and the inductor in parallel. Well, no matter, we can solve this using the potential divider equation as well. This time our output is across an effective impedance of the inductor and the capacitor in parallel, which is given by this term here. The total impedance in the circuit is this term plus R, and if you do a bit of algebra on this, we'll end up with this. Now you may recognise that. That's the bandpass filter characteristic again. We've got a single zero at 0 Hz, and we've got two poles which we can express in terms of a resonant frequency and a Q factor as before. So this is just going to give us a bandpass filter characteristic. But it's not quite the same characteristic as we saw before. If you compare them, you'll note that in both cases the term on the numerator is the same as the term in j omega in the denominator, and the resonant frequency is the same. It's 1 over the square root of LC in both cases. It's the frequency where the impedance of the capacitor and the impedance of the inductor cancel each other out. But the Q factor is different. If you look carefully, you might notice that the Q factor is inverted. The Q factor of this circuit is 1 over the Q factor of this circuit. So if we designed these components to have a Q factor of 10, then this circuit would have a Q factor of 0.1 if you built it with exactly the same components. We can produce something quite different to the ones we've seen before, though. Just again with 3 components. This time we're taking the output across the capacitor, as we have before, but we've put the inductor and the resistor in parallel rather than in series. Once again, analysis fairly straightforward. It's just the potential divider equation and a bit of algebra, and you produce this. Very familiar form on the denominator. It's 2 poles, second order, and we could express the resonant frequency once again as 1 over the square root of LC. And we could work out the Q factor because we know from the term in j omega, which is j omega over omega naught, that here is j omega L over R. Therefore we have Q omega naught of R over L, and Q equals R over L omega naught, which is R over L times the square root of LC, and we would usually write that as R times the square root of C over L. This type of result and form keeps coming up over and over again. What's different this time is the numerator. We've got a 0. There is a value of j omega for which the numerator is equal to 0, but it's no longer at 0 Hz. It's at a finite frequency. This means that a lot of the results that we've derived before no longer apply. You can derive similar results for this circuit, but once we start getting away from the straightforward case of a resistor, a capacitor and an inductor in series, we usually go to simulation to work out what's happening. And if we simulate this one, we get this response. We've got a low frequency gain of 0 dB. We can get that just by looking at the expression for the frequency response. J omega L over R over 1 plus J omega L over R plus J omega squared over, rather J omega squared times LC at the moment. Haven't converted it into Q and the resonant frequency. And we can see that at low frequencies, when omega is 0, this is just going to evaluate to 1 over 1, which is a gain of 1 or 0 dB. So we'll start out 0 dB. We're going to get to 2 poles and 1 0. With the particular values of the circuit that we've got here, the poles are complex, and they give us a resonant peak around about the resonant frequency. And it starts to head down at 40 dBs per decade, but then the zero comes into play and it kind of flattens a little bit and ends up going down at 20 dBs per decade. And you can see the kind of bend just about there in the Bode plot, where the zero cuts in, and it reduces the slope from 40 dBs per decade around here to about 20 dBs per decade at very high frequencies over there. The final one I'm going to look at is this one. I've now got the capacitor and the inductor in parallel, and the output being taken across a resistor in series with that parallel combination. Well, I can analyse this circuit just using the potential divider equation and the formula for two components in parallel as I have before, do a bit of algebra, and this is the result that I would get. So I've now got two zeros. I've got a quadratic on the numerator as well as on the denominator. And if I work out where those two zeros are, well, those two zeros are the values of j omega for which the numerator is equal to 0. So, in this case, they would be given by j omega squared equals minus 1 over LC. J omega is therefore the square root of minus 1 over LC, or plus or minus it, because I've got two zeros. So j omega is plus or minus j over LC. They are purely imaginary zeros. If I was to plot those zeros on the Argand diagram, real axis, imaginary axis, the zeros would be here and here. Now, if you remember that sort of graphical visual model we had with poles as sticks going up from the ground and zeros as tent pegs fixing the canvas to the ground, and the height of the canvas being the amplitude response, then that indicates that at these frequencies we're going to get nothing. Nothing coming out at all. The canvas is fixed by a tent peg to the ground at that point there. Our poles, on the other hand, they may be real, they may be complex, but they're not on the imaginary axis. They might be, say, somewhere there and somewhere there. So what we would expect the frequency response to do would be to start off at 0 dB, because if we look at this expression here, we can see that if omega is 0, that's just going to give 1 over 1, or 0 dB again. You can also see that it's going to end at 0 dBs as well. Because if omega is very large and tending off towards infinity, then these terms in the denominator are going to be negligible compared to this one, and the 1 in the numerator will be negligible compared to this term. These terms will therefore dominate. We'll end up with an approximate value at high frequencies of the frequency response as just j omega squared LC over j omega squared LC, and that's just equal to 1 again, or 0 dB. So this frequency response is going to give me an amplitude response which both finishes and starts at 0 dB. In between, we're going to hit a poles break frequency, start heading down. We're then going to hit the frequency of the zero. But the zeros are on the imaginary axis, so they're not going to tilt us up by 20 dBs per decade. They're going to force the frequency response down to infinity. And then it's going to come back up once we get past the frequency of the zeros. And at this point here, we'll be going up at 20 dBs per decade, because we've got the effect of both zeros and one pole, until we get to the second higher frequency pole. That's going to round us off, and we're going to carry on horizontal from there. And we're going to get a frequency response something like this. Always label the axis. And you can see that in the simulator as well. With some typical values, it might look something like this. It's called a notch filter. They're quite useful if there is one particular frequency of interference that you want to get rid of from your signal. They could effectively remove a very narrow range of frequencies and leave all the other frequencies untouched. That's everything about second order frequency responses for now. Next topic is possibly the hardest topic in the whole module. Second order step responses.